This video is going to discuss indefinite integrals and properties related to indefinite integrals. The indefinite integral is another way of communicating an antiderivative. Okay, and the notation that goes with it is the following. So this symbol right here, this is called an integral sign. Okay. And what this communicates to us is that this is an indication to find the antiderivative of whatever follows. So this next piece in here, this is an integrand. That is what you are trying to find the antiderivative of. The dx, this is a bit of notation, okay, for us right at this level. What this is telling us is what variable you are trying to anti-differentiate. Okay, there could be instances not necessarily at this level, but there might be instances where you are trying to find the antiderivative of a function that has many variables. Okay. So integral, integrand, and then the whole expression here, this is an indefinite integral. Cool. And so what this notation produces is, over here, this is an antiderivative. Okay, so all this notation is just communicating mathematically, hey, find the antiderivative of little f, and you get out the antiderivative on the other side. Okay, and the way we read this is the integral, okay, integral, and this looks kind of like an elongated s. Integral of f of x with respect to x is capital F plus c, or we could say the antiderivative of f of x with respect to x is that. Okay, so here we are not finding any specific values of x nor c. So the output of an indefinite integral is always the general antiderivative without any values of c specified. Okay, so just some quick examples here. We have the integral of 2x to the power of 3 halves, and only, just to clarify, only the x is to the power of 3 halves, not the 2. Otherwise, the parentheses would be different. Okay, so to find the antiderivative, okay, the antiderivative x, I have to increase the power by 1, okay, 2, and then divide by the power. So divide by 5 halves, and remember my constant, and simplifying all this, this ends up being 4/5 x to the 5 halves plus c. Okay, if the simplification is easy, do it. Okay, and for the antiderivative of 7 to the t, this one you might have to refer back to a formula sheet, but this is going to be 7 to the t times 1 over the natural log of 7 plus your constant. Okay, and you can leave it like that. Okay, so just some practice with the notation. And now, in terms of properties that go along with an antiderivative, same sort of thing as differentiation. If we're trying to find the integral of, or the antiderivative of a sum or difference, we can find the antiderivative or the integral of either of both pieces separately first and then add them. Similarly with a constant, if we have a constant inside there, we can pull it outside and just worry about the antiderivative of the function itself. Okay, so for examples here, I'm going to do a little bit of work. You don't necessarily have to show all this work, but this is going to be equivalent to, okay, so I can do the integral of each individual piece, and I'm going to do the constant multiple at the same time. So 4 times the integral of 1 over 3, or the cube root of x dx. And now this notation dx, you do need it every single time you have an integral. Okay, if you have an integral, you need a dx. And then minus 2 pi is a constant, so I'm going to pull it outside of the integral. And then sine of pi x is going to be inside dx, integral dx, plus 4 times the integral of e to the minus 2x dx. Okay. Finding the antiderivative of each of these pieces, this I can express as x to the minus 1/3 power. Okay, so if I find the antiderivative of each piece here, it's going to be 4 parentheses, and then the antiderivative of x to the minus 1/3, so I have to increase the power by 1 and divide by the power. Okay, and then I'd normally add a constant. I'm going to add only one constant at the end because I'd add them all up anyway. So I'm going to ignore the constant until the very end. Minus 2 pi, antiderivative sign is, let's see here, it's going to be a minus cosine of pi x, and then by the chain rule I'd have to multiply by pi, but instead to undo that I need to divide by pi. Plus 4, and then the antiderivative of e to the 2x is e to the minus 2x times 1 over the derivative of the exponent. Okay, and then all of that is plus c. Okay, and I encourage you at this point to simplify this answer a little bit. It does simplify rather nicely. I'm not going to spend the time in the video to do so. Okay. If you have any questions about the antiderivatives, I also encourage you to go back and revisit that, or revisit the video on Introduction to Antiderivatives and review the table listed in that video. Okay. And then the last example for this video is going to be the following. So it's the integral of a over 2, or plus 2 over y plus secant squared of all that stuff. Okay. And notice that we are finding the antiderivative with respect to y. Okay, so again, I'm going to break it up. So I'm going to find the antiderivative of a with respect to y plus and then this is going to be 2 over y dy plus integral secant squared of pi y over 2 dy. Okay. Now this first one, this is just a constant. Okay. So I integrate a constant, the constant stays there, and then I'd have to find the antiderivative of 1, which by the power rule is just ay. Okay. This next one, the 2 is a constant, so I'm going to just leave that alone. And then it is the same as 1 over y, and the antiderivative of 1 over y is at natural log of the absolute value of y. Again, make sure to have absolute values with natural log, just so we don't run into domain issues. And the antiderivative of secant squared, well, that's going to be tangent of the input. Okay, but then normally when we differentiate, I would have to multiply by pi over 2. When I anti-differentiate, I divide by that pi over 2. Okay, and then always remember the constant that's hanging around at the end. Okay, so that is an indefinite integral using the different properties.